Okay, look, so 3-eye atlas. Right off the bat, this object is weird. And when I say weird, I mean the kind of weird that makes you stop and reevaluate assumptions you've had your whole life about. You know, how predictable physical systems are. I don't want to be melodramatic, but it's the kind of thing that makes you squint at data and then squint again like, are my eyeballs broken? Or is the universe trying to show me something I wasn't expecting? So what do we know? We know it's interstellar in origin, that much is clear, meaning it didn't form in our little local gravitational playground. It was born elsewhere, and it came into our neighborhood. Okay, fine, big deal, right? We've had interstellar visitors before, so the headlines will say, another interstellar comet, nothing to see here. But the headlines are lazy, they try to squeeze complex phenomena into tidy boxes. 3-eye atlas doesn't fit the tidy box. First, brightness. The photometry is noisy in a way that's like insistently noisy. It flares, then it dims. Then it has these plateaus where it sort of sits at a brightness that doesn't make sense for a simple spherical or irregular rock with a thin coat of ice. Sometimes it behaves like it's releasing gas, jets, plumes, whatever. But then the timing of those outbursts doesn't correlate cleanly with perihelion or solar heating angles. So you've got to ask, if it's outgassing, what's driving the outgassing at those times? If it's not outgassing, what's making the brightness change? Then there's the albedo and composition estimates. Spectra are tricky at those distances, low signal to noise, blah blah, but there are hints. Hints that the surface properties are heterogeneous, maybe layered, maybe a mix of refractory material and volatiles in ways that aren't typical. Think of it like a weathered spacecraft hull that's been in interstellar space for a long time, micrometeorite pitting, radiation scars, combined with regions that respond to sunlight like ice would, but only sometimes. That's weird. Trajectory. Okay, trajectory. Orbital mechanics is merciless. If you give me precise initial conditions, I can predict a path years into the future. Tiny forces matter. Solar radiation pressure, outgassing jets, gravitational tugs from known bodies, we can model those. And with 3-eye atlas there are tiny, persistent deviations from the simplest model. Not huge, minuscule, but persistent, tiny non-gravitational accelerations. And when you start chasing tiny, persistent accelerations, you need to be honest with yourself. Are they measurement error or are they real? And if real, what causes them? Now there are mundane hypotheses. We should always begin with the mundane. Maybe it's a porous aggregate with asymmetric outgassing. Maybe it's an odd composition with embedded volatile pockets that vent episodically when they reach critical temperatures. Maybe rotating, irregular shapes produce asymmetric thrust, all possible, totally plausible even. But sometimes the mundane explanations fail to explain all the facts in aggregate. And when that happens, you have to entertain alternatives, not as in aliens, screaming in font 72, but as careful skeptical scientists would. List hypotheses, weigh them, test them. One possibility that remains on the table until we can rule it out is that the object exhibits properties more consistent with an engineered object or an object influenced by technology than with a natural comet. And I want to be careful here. Engineered does not necessarily mean intelligent alien civilization waving neon signs. Engineered could mean any number of things. It could mean debris from an artificial structure. It could mean a probe. It could mean a passive reflector with unusual materials. It could mean a fragment of something much larger. The space of engineered possibilities is wide, and while it's a big claim, it's worth considering because the data nudges you in that direction if you take the anomaly seriously. There's also the timing and the pattern to consider. Oumuamua, then Borisov, then other visitors now. 3-eye atlas. You start to notice patterns when you have 3 data points. Patterns could be coincidence. Patterns could be selection bias. We are better at spotting these things now, so more of them get cataloged. That's a fair point. But another possibility is that there's an interstellar phenomenon or a technological deployment that produces multiple objects along similar vectors. Think of sending probes as a civilization spreading strategy. Send scouts, send debris, send decoys, send weather stations. If you had a probe system designed to explore stellar neighborhoods, you might see multiple objects on related trajectories as part of that distribution. It's a thought experiment worth keeping in mind. Okay, let's talk about the specifics of the anomalies in greater detail, because you can't just float the words anomaly and expect anyone to be satisfied. There are 4 classes of anomalies that, taken together, make the object interesting. Number 1, temporally inconsistent activity. The object displays activity that doesn't sync with straightforward radiative heating. There are flare-like brightenings at distances where, if this were a comet made mostly of water ice, you wouldn't expect much sublimation. Now, comets can carry supervolatile ices that sublimate at low temperatures like CO or CO2, so that's a possible natural explanation. But supervolatile-driven activity tends to have characteristic spectral signatures and a certain statistical behavior. 3-eye atlas does some things that look like that and some things that don't. Number 2, reflective behavior. There are brief periods where the object's light curve suggests a higher reflectivity than the average. It's not sustained and it's not uniform, it's patchy. Patchiness could be a layered surface with different materials, or it could be a thin sheet of something reflective catching light. At certain angles, thin sheets, think membranes, produce very different radiation pressure signatures than lumps of rock. If you have a thin membrane, even a low mass-to-area ratio, the solar photon pressure can produce accelerations comparable to small non-gravitational anomalies we observe. Number 3, rotation and tumbling dynamics. The rotational state appears complex. There are hints of spin variability and precession that are difficult to reconcile with a compact monolithic body of a single material. Complex rotation can result from asymmetric mass distribution or from torques induced by outgassing jets. But again, the timing and correlation with brightness changes sometimes don't quite match. Number 4, trajectory correlation with previous interstellar visitors. This is subtle, but it's there. When you project inbound asymptotes back through interstellar space, some alignments seem more than random. It's not a smoking gun. It's a needle of curiosity in a haystack. If you had to place a bet, and I'm not advocating betting markets for space mysteries, you would say the alignment is interesting enough to warrant follow-up modeling. Could these be fragments from a common source? Could these be probes dispatched along a preferred route by a civilization in a different star system? Could they be the byproducts of some interstellar engineering project? All possible. Let's talk about detection limitations, because people underestimate how much uncertainty instrumentation adds. Telescopes are incredible, but they have blind spots. Detection thresholds bias us towards certain sizes and brightnesses. We are now in a regime where small, low-mass, high-area objects can be detected if they scatter light in particular ways and if survey cadence catches them. So the population we observe is not a true representation of what's out there. It's a very skewed sample. That means hypotheses about commonness or rarity must be tempered by detector bias. Now imagine a hypothetical engineered object designed to be stealthy. Stealthy in what sense? Stealthy in the electromagnetic signatures it presents, maybe cloaked by materials that absorb in certain bands, or designed to look like random noise in the visible but have structure in the infrared. If an engineer wanted to be unseen by a given observer type, they might choose a spectral signature that's suboptimal. For our surveys, conversely, if something is designed to be seen selectively by certain sensors, it might appear erratic to us. The point here is not to assert malice or intent, it's to point out that a wide range of design behaviors could mimic the oddities we observe. I want to step back and say something larger. There's a philosophical temptation in these moments too. Either snap to extremes, claim alien visit, or claim data artifact, and both extremes are bad science. Good practice is to keep a balanced posterior, update gradually, apply Occam's razor sensibly, favor simpler explanations but don't ignore contrarian evidence. Also, run experiments. The right response to a tantalizing anomaly is to collect more data, to model, to try to reproduce signatures in the lab, to design missions that could intercept or chase. In other words, be proactive. Which brings me to the practical side. If 3i Atlas were worth chasing, how would we chase it? We have a couple of choices. 1. Rapid response small missions, CubeSats piggyback rides on existing launches, kinetic chasers using high ISB stages. 2. Plan for more patient, larger missions that could rendezvous if an object's trajectory is favorable. 3. Remote sensing campaigns coordinate observatories across bands, radio, infrared, optical, ultraviolet, maybe polarimetry to see surface textures. And 4. Use in situ experimental hardware when possible. Imagine a tiny impactor or a close flyby probe with spectrometers, mass spectrometers, dust analyzers. These are not trivial, but they're increasingly feasible. A word on radios and beacons. People always ask, would it transmit? If it were engineered, would it try to communicate? Not necessarily. A probe could be passive, a scout, or it could be transmitting in narrow bands we don't commonly monitor, or it could be using communication modalities we do even think to look for. Detection of an engineered signal would be, obviously, a game changer, but absence of an obvious signal does not imply absence of engineering. Engineering can be quiet. Let's talk scale. Suppose you found that 3i Atlas was a fragment of a larger object or an artifact from a technological event in another system. What does that mean for us? Practically, it would be profound, but not necessarily in the dramatic, aliens are here sense. It would mean that technological processes occur elsewhere in the galaxy. It would change our priors on the frequency of certain technological behaviors. It would inform models of how technologies survive interstellar transit. Do we see a lot of debris? Do we see little? Are probes one-off or part of swarms? On the flip side, if 3i Atlas is a natural object with previously unknown properties, that's equally revolutionary for a different reason. It would mean our models of small body physics need updating. Maybe chemistry in interstellar space produces unexpected composite materials or structures. Maybe radiation processing over millions of years produces layered microstructures that mimic artificial surfaces. That's fascinating too. Both outcomes are fascinating because both expand our knowledge. I keep saying we should be proactive, so let me be explicit about a few concrete steps that would accelerate understanding. First, increase survey cadence and diversify spectral coverage. We need more eyes more often across more wavelengths. Second, build a rapid response small probe architecture. Standardized interstellar chase CubeSat packages that can be attached to high-energy upper stages and sent after targets with minimal prep. Third, invest in laboratory replication. If the brightness anomalies might be caused by thin membranes or exotic ices, try to produce the same light curves in lab conditions. Fourth, open data. Share the raw photometry, encourage cross-validation, encourage independent teams to reprocess the data. I know bureaucracies and institutions have constraints, funding cycles, review boards, risk aversion. But the cost-benefit analysis for a few million here and there to investigate such an object is compelling. Not everything needs to be a billion-dollar mission. A lot of progress can be made with coordinated ground assets and smaller space assets if we can act quickly. I also want to talk about narrative and culture because how we frame discoveries matters. If the media screams alien at every ambiguous signal, two things happen. One, the public gets burned out by false alarms. Two, serious research is trivialized. Conversely, if scientific institutions are reflexively opaque, the public imagination fills the void with conspiracy. Transparency and cautious curiosity are the antidotes. Present the anomalies honestly, present the uncertainties honestly, and avoid sensationalism, while also not hiding the intellectual excitement. Now, a personal aside. There's an emotional texture to this kind of discovery that people don't always talk about. When you realize the universe has more surprises, you feel a strange mix of exhilaration and humility. Exhilaration because the cosmos is richer than you thought. Humility because your models were incomplete. That's the best feeling for a scientist or engineer. It's the feeling that tells you you're on the cusp of learning something new. Back to the object. If I had to give a qualitative assessment today with current data, I'd say probability. It's purely conventional natural comet asteroid, still the leading hypothesis, because nature is tricky and abundant. Probability, it's an anomalous natural object exhibiting physics or chemistry we haven't characterized. Meaningful, maybe substantial. Probability, it's engineered, non-zero, interesting, and worthy of follow-up. The key is not to prioritize one explanation for narrative reasons, but to prioritize follow-up mission design and diversified observation, so we can shift those probabilities toward certainty. Finally, let's talk about what this means for us as a species. If interstellar objects like 3I Atlas are common, and if some fraction are technological, it suggests the galaxy is a place where technological artifacts can traverse and survive, at least transiently. That has implications for how we think about our future in space. Should we build durable artifacts that can survive for millennia? Should we design self-preserving information capsules? I think yes. Even if every interstellar object turns out to be natural, the exercise of thinking about robust interstellar artifacts makes our engineering better. It pushes us to design for longevity, for graceful degradation, for redundancy. And one more thing, curiosity is recursive. The more we look, the more we find, and the more questions we have. That means funding, education, international cooperation. Scientific curiosity is one of the few things that benefits from global collaboration. We should make it as global as possible. Share data, share missions, share credit. That's how we accelerate discovery. So 3I Atlas is a puzzle. It's an invitation. It's a mirror that shows both our ignorance and our potential. It's messy, it's fascinating, it's slightly unnerving, and it's exactly the kind of thing that should make us get off our chairs and build better instruments, send smarter probes, and keep asking hard questions. Not because we want dramatic headlines, though those will come, but because the universe is there and it's talking in a language that is subtle, and I think we're finally learning to listen. Look, okay, one last pragmatic note. If you're a scientist working on this, don't be shy. Publish the weird bits. If you're an engineer, sketch cheap, fast interceptors. If you're a student, learn orbital mechanics and signal processing. You'll be useful. If you're a funder, fund both the instruments and the people who can think about weird stuff without getting ridiculed. The history of science is full of moments where curiosity paid off in ways people didn't predict. This could be one of those moments. All right, that's the long and the short of it. 3-Eye Atlas is interesting, probably natural, possibly more, and absolutely worth investigating. It's a mystery that rewards steady, careful attention. And by the way, even if the answer turns out to be mundane, the route we take getting to that answer will make us smarter, stronger, and better equipped to explore the cosmos. So let's go do that. Let's build the tools, run the observations, and figure it out.